the European Social Class for Molecule Research, CERN, is uncovering subtleties of one more particle, the smasher. Today, on various occasions, it is more significant and twice as fundamental. It has seen 3 new particles that could be useful in figuring out how our universe was imagined and what its future appears to be. Researchers at CERN have of late uncovered divulgences that turn how we decipher the universe on its head. Under the external layer of their enormous tests lies a colossal spread of particles and controls so curious they could be straight far away from possible parts to substitute perspectives. Particles that challenge the genuine explanation of the true. What stupefy advantaged bits of knowledge are confidential inside these tests? Could we sooner or later skip into the universe of CERN and relax the bits of information that could reconsider our universe? The section to new marks of view, a wormhole, could theoretically show up out of nowhere above, and the explanation would be the remarkable evaluations driven at CERN, home of the Colossal Hadron Collider, LHC. The LHC is the world's largest and most powerful molecule smasher, viewed as close to Geneva, riding the line between Switzerland and France. There are advantaged secrets about this uncommon association that the world doesn't have, some association in insider facts that could change how we view material science. In actuality, the universe CERN, the European Association for Atomic Investigation, works this enormous, unsurprising instrument. It connects in excess of 27 kilometers and sits critical underground. The motivation behind the Colossal Hadron Collider is to give physicists the capacity to test the assessments of different theories in molecule material science. This hardens the high-profile appraisal of the standard model of molecule science, which helps us in figuring out the essential structure blocks of the universe. At its center, the Goliath Hadron Collider works by speeding up protons to essentially the speed of light before beating them together. These impacts produce a shower of new particles, which study to get bits of insights into the guidelines of nature. It was through such starters that the Higgs boson, much of the time alluded to as the God particle, was discovered in 2012. This transparency bore witness to how particles get mass and was a huge moment in nuclear material science. The tests driven at the gigantic Hadron Collider are fundamental for figuring out attributes that happen under ridiculous circumstances, basic vague from those not long after the Big Bang. The information added up to can fill us in more about how the universe begun, evolved, and about the basic constituents of matter. This makes the gigantic Hadron Collider a player in possibly revealing new bits of reality, including dark matter and the central forces of nature. Such high-level trial and error at CERN doesn't come without worries. Some estimate about high-energy tests making dark holes or intriguing matter that could present dangers to Earth. Anyway, CERN guarantees that all safety measures are met, and prepared specialists closely monitor these examinations. Studies on theoretical models confirm that any unsafe conditions are incredibly improbable. Through its steady appraisal and exposures, CERN helps us figure out the universe better and demonstrates the surprising limit of human movement and joint exertion in seeking information. The LHC is humanity's continuous powerful event. The astounding Hadron Collider at CERN isn't simply an unimaginable piece of innovation. It is a wonder of present-day science and engineering. Worked with under the Swiss-French line, the Colossal Collider goes through a tunnel 27 kilometers in width and is fundamentally pretty much as critical as 175 m underground. This makes it the best particle collider on the planet and one of the chief instruments in the field of particle material science. The movement of the Colossal Hadron Collider is intended to make DOE assessing critical scale. The head ring of the collider, housed in a tunnel with a breadth of 3.8 m, contains 2 connecting equivalent beam pipes. Each line arranges protons in the opposite direction, quickly propelling them with a series of superconducting magnets. These magnets are fundamental for maintaining the proton's course at speeds near that of light. Integrating the beam pipes are layers of cooling structures that keep the temperature colder than space, required to keep the superconducting magnets at their working temperature. The size of the massive Hadron Collider is additionally underlined by its use of extraordinary magnets, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to focus them. The best and most powerful superconducting magnets used are 15 m long and weigh 35 tons each, showing the massive scale and technological aspirations behind the collider. The principal goal of the Gigantic Hadron Collider is to explore the wonder of bits of the universe by seeing the smallest pieces of matter. By speeding up particles to essentially the speed of light and consequently colliding them, the Gigantic Hadron Collider allows physicists to zero in on the next particles created during these impacts. This cycle helps in testing and expanding our understanding of the standard model of molecule science, which is the best depiction of the subatomic world. One of the imperative targets behind the enormous Hadron Collider's tests is to uncover the insider facts of the Higgs boson. Its discovery at CERN in 2012 confirmed hypotheses about how particles acquire mass. The Gigantic Hadron Collider, moreover, examines other central particles and forces, attempting to answer critical questions like the presence of dark matter and the nature of the universe shortly after the Big Bang. The enormous Hadron Collider needs to confirm the presence of new particles that speculative material science predicts yet has not yet observed. These assessments are key for possibly finding new physics beyond the standard model, including supersymmetry and aspects beyond the ordinary three-dimensional viewpoints. The vision behind the amazing Hadron Collider isn't just to figure out the universe's plan, but also to support global cooperation, with numerous specialists from over 100 countries participating. The immense Hadron Collider is a confirmation of overall collaboration in the quest for knowledge. Its design and scale enable it to deal with the most serious demands in material science. Its reason stretches beyond simple intellectual curiosity, aiming to encourage how we unravel the universe and support worldwide participation in science. Through this massive and complex device, humanity continues to expand the limits of what is known and experienced in the quantum realm. But how does the huge Hadron Collider truly work? At the center of CERN's examination facilities, the colossal Hadron Collider functions as a strong improving point of intermingling into the quantum space, permitting experts to see and study the fundamental particles that make up everything in the universe. The process of particle speed increment and collision at the huge Hadron Collider is a critical method for testing the underpinnings of material science. Inside the collider, two high-energy particle beams travel at essentially the speed of light before they are made to collide. These beams travel inside tubes kept at ultra-high vacuum, mimicking the conditions of space. Superconducting electromagnets chilled to temperatures colder than space help steer and concentrate the beams at allotted collision points along the path. These beams apply huge energy as they slam into particles, creating a collection of subatomic particles, some of which are incredibly unstable and exist for only parts of a second. To recognize and analyze the results of these impacts, the massive Hadron Collider is outfitted with enormous detectors: ATLAS, CMS, and LHCb. Each detector is designed for specific types of analysis. These detectors cap information about the particles, including their mass, charge, and energy. This data assists physicists in testing assumptions for molecule material science theories, including the standard model, and exploring particles and forces that govern the universe. One of the crucial discoveries at the Gigantic Hadron Collider was the discovery of the Higgs boson in 2012. This particle, sometimes referred to as the God particle, is significant because it provides proof for the Higgs field, which is responsible for giving mass to fundamental particles. The presence of the Higgs boson was predicted by the standard model, and its discovery was an extraordinary accomplishment, confirming long-held theoretical expectations. Beyond the Higgs boson, the Gigantic Hadron Collider has also been instrumental in discovering a range of different particles. For instance, the collider has provided evidence for the existence of pent quarks and confirmed the presence of tetraquarks, particles comprised of 4 and 5 quarks, respectively. These discoveries expand how we might interpret hadronic matter, which is matter made of quarks bound together by the strong force that holds nuclear cores intact. These discoveries demonstrate the power of the standard model and open new avenues of exploration in particle material science, offering insights into the behavior of matter under extreme conditions such as those not long after the Big Bang. Hypothetical dangers, such as strangelets or microscopic black holes, have been subjects of public interest and continuous evaluation. Strangelets are a theoretical kind of matter that is more stable than normal matter. The theory suggests that strangelets could convert any matter they come into contact with into strange matter. The fear surrounding the theory is that if strangelets were created during particle collisions at the LHC, they might potentially convert the Earth's matter into strange matter. However, broad evaluations and security studies led by CERN and the global academic community have addressed these concerns. Studies have shown that even if strangelets exist and were created at the LHC, they would most likely be very unstable and decay too quickly to have any effect on Earth's matter. Furthermore, high-energy astronomical rays, high-energy particles from space, constantly hit Earth with energy levels much higher than those produced by the gigantic Hadron Collider without creating any oddlets. This regular evaluation suggests that strangelets are not a significant risk. The worry that the gigantic Hadron Collider could create small black holes comes from hypotheses about additional dimensions in physics. Some theoretical models suggest that high-energy collisions inside the LHC could create tiny black holes that would vanish immediately due to a process called Hawking radiation, named after physicist Stephen Hawking. However, experts agree that if tiny black holes were ever created at the LHC, they would pose no threat to Earth. The ongoing work at CERN and the enormous Hadron Collider has expanded our understanding of particle material science and revealed the extraordinary range of potential discoveries. The Large Hadron Collider (LHC) operates as one of the most ambitious and intricate scientific instruments ever constructed, providing physicists with the ability to explore the very foundations of the universe. Since its construction, it has pushed the boundaries of our knowledge, revealing new particles, forces, and potentially undiscovered aspects of physics. One of the central goals of the LHC is to probe the potential mysteries hidden within quantum mechanics and high-energy physics, areas that were previously inaccessible. At the heart of the LHC's groundbreaking work is its ability to recreate conditions similar to those that existed just moments after the Big Bang. This is achieved by accelerating protons to nearly the speed of light and causing them to collide with one another, which results in the production of a vast array of particles. These particle collisions are crucial for testing existing theories and for providing insight into unknown realms of physics. The LHC enables the detection of phenomena that are exceedingly rare, and these observations often challenge preconceived notions about the universe. The experiments at CERN are not only focused on confirming the predictions of the standard model of particle physics, but they also aim to investigate the fundamental questions that remain unanswered. For example, one of the most pressing mysteries is the nature of dark matter, which makes up about 27% of the universe's mass-energy content. While it exerts gravitational effects on visible matter, it does not interact with electromagnetic radiation, making it invisible to traditional detectors. CERN's research could lead to breakthroughs in detecting and understanding this elusive substance. Another key focus is the exploration of supersymmetry, a theory that proposes a symmetry between two basic types of particles, bosons and fermions. Supersymmetry suggests that each particle in the standard model should have a heavier superpartner, which could help explain several phenomena, including the existence of dark matter. The LHC could potentially uncover evidence of these supersymmetric particles, opening up new avenues for understanding the fundamental forces of nature. In addition to fundamental physics, the LHC is advancing our knowledge of particle interactions at the smallest scales. By analyzing the products of proton-proton collisions, researchers are able to study rare and transient particles, such as those involved in the weak force. The weak force governs radioactive decay and plays a critical role in stellar processes, like the fusion reactions that power stars. By understanding the weak force in greater detail, scientists hope to uncover new particles or interactions that have yet to be observed. Moreover, the LHC's work extends beyond particle physics, contributing to advancements in technology and other fields. The technological innovations developed for the collider, including advanced cryogenics, superconducting magnets, and data processing systems, have broader applications. For instance, the World Wide Web was invented at CERN as a tool to share and analyze data generated by particle collisions. The LHC has also spurred improvements in computational techniques and particle detectors, which could benefit fields such as medicine, material science, and environmental research. The international collaboration involved in LHC experiments underscores the global significance of this research. With contributions from over 100 countries, the LHC exemplifies the power of cooperation in science. The exchange of knowledge and expertise between scientists from diverse backgrounds enriches the work being done at CERN. The data collected from LHC experiments is publicly available and is shared with researchers worldwide, facilitating further discoveries. Despite the immense success and discoveries of the LHC, its work is far from over. Future upgrades and advancements are planned to increase its energy and luminosity, allowing researchers to probe deeper into the subatomic world. As new technologies and experimental techniques are developed, the potential for further groundbreaking discoveries grows. Whether it's uncovering new particles, verifying theoretical models, or addressing the unknowns of the universe, the LHC remains at the forefront of scientific exploration. Through its revolutionary research, CERN continues to redefine our understanding of the universe, not only in terms of its past but also in terms of its future. Every experiment at the LHC brings physicists closer to unraveling the most profound questions about the cosmos, and the answers may ultimately reshape our conception of space, time, and matter itself. The journey through the quantum realm is far from complete, but the LHC is providing the tools and insights necessary to explore it further.